structure of unit ball in Banach space n star, which is B of n comma f. So S star, which is the unit ball, the symbol which is used, is collection of all those f belonging to n star such that norm of f is less than equal to 1. So f is a map from n to f linear, continuous, and the norm of f is given to be the supremum norm is the supremum of mod of f of x upon norm of x belonging to n, x not equal to 0. And here we are looking all those f in n star whose norm is less than equal to 1. So this object is less than equal to 1. So we are going to focus on S star closed unit ball. We will try to see what kind of topological properties this has. As I said, what kind of structures are there on S star with respect to what? So the n star with respect to the topologies on n star. So one particular of interest is the weak star topology. So we have seen the weak star topology on n star, which was generated by this kind of basis element S, X, F naught, epsilon, where epsilon is a real number greater than 0, F naught is an object in n star, X is an object in n, and this was what? Collection of all f belonging to n star such that mod of f of x minus f naught of x is strictly less than epsilon. So this forms a sub basis for the weak star topology. Essentially, we had the n star star, the identification of n as an injective map in n star star, x going to f subscript x. A star is a compact Hausdorff space in the weak star topology on n star. This is what we are interested in proving. So this is a proposition. So So the closed unit ball. So what we are trying to say is that the closed unit ball in N star is compact and Hausdorff. It's a closed set. S star is a closed set as well as it is a bounded set. So let's try to prove this proposition. So we'll use some ideas from topology, a little bit points of topology and additional material, or rather an advanced material which you have seen, Tikhonov's theorem, product topology, subspace topology, and so on. We have shown that if you take epsilon is equal to fx minus gx modulus, where if f is not equal to g in N star, there existed x belonging to N such that fx not equal to g of x, and then the difference is there, and this is epsilon by 3. Then what do we have is that this distance is that if you take the epsilon by 3, take the basis s x f comma epsilon by 3 s x comma g comma epsilon by 3, then what do we have is that these two bases are the s x comma f comma epsilon by 3 intersect with s x comma g comma epsilon by 3. This is what set? This is an empty set. So in fact, it's a Hausdorff space. We have already shown that N star is in fact a Hausdorff space. So S star is having the subspace topology on it. So if S star is having it's a subspace, then subspace topology on S star is coming from N star. So every open set in S star is in fact intersection of an open set in N star with S star. And we know that subspaces of Hausdorff spaces are Hausdorff. As you can clearly see that every basis element is an sub-basis element is an open set. So if you take intersection with S star also, what do we get is that these two are disjoint set because their original sets are disjoint. So their intersection with S star also are pairwise disjoint. So if it is disjoint, so that is a distinct neighborhood. So S star clearly is Hausdorff space. In subspace topology, what we are interested is that only the thing that remains we need to show is that S star is a compact set. Or a compact space rather. Closed subspaces of compact spaces are compact. This is another proposition we have proved, so we'll use that fact also. So we'll try to show that S star is closed in the weak star topology. Since closed subspaces of compact space are compact. So we will define an embedding of a star in a compact set space, and that embedding is, and we further show that a star is compact subspace, rather closed subspace, so hence it would be a compact closed in the embedded, in the topology of the embedded space. So a star, by definition, is collection of all those f belonging to n star such that norm of f is less than equal to 1. So what do we get? If a star is collection of all those f in n star such that norm of f is less than equal to 1. So a star is having vectors which are having the supremum norm. So this norm of f is a supremum norm. The supremum norm, which is as you have seen, supremum of mod of f of x upon norm of x, where x belongs to n and x is non-zero. So all those things, we have this S star. Once we have that this is less than equal to 1, so this clearly implies that mod of f of x is less than equal to 1 times norm of x for all x belonging to n, if f is in S star. That we have. So the point is that as an so if this is a real, if n is a real vector space, then what do we have? Real vector space, then it's just absolute value. So minus norm of x is less than equal to f of x is less than equal to norm of x. This is what we have. Okay. So minus norm of x is less than equal to f of x is less than equal to norm of x in case of this n is a real vector space. So f of x for this one particular x, so this is true for all x, so any particular x you take, and so if f is in S star, this is satisfied. So f of x belongs to what interval? It belongs to the closed interval minus norm of x comma norm of x. So this interval f of x belongs. Okay. So if we vary, so what the point is that a function f is this f over here is a mapping from n to the field f, where f is a real in this case. It's a real vector space, at least for this case. So what do we get is that for a one particular x, we are getting a value whatever that is in between these two numbers less than equal to. So what do we get? Norm x and so on. So lying between these 2 points. So if you take this x, it is I have this f of x is one particular value. As you change your x, it would suppose there is another point y. So what happens to this f of y? F of y belongs to the closed interval minus norm y to norm y. So exactly one value between this thing. So you can think of this f as an array of points lying between these intervals. So x is there, it is lying minus norm x to norm x. If y is there, it is lying to minus norm y to norm y. If it is z, minus norm z to norm z, and so on. So you take multiplication of all of this thing, so of the spaces, and then we try to put a topology on that. It would be the following. The product of, so if you look, let's call Cx with this is minus norm x to norm x, and so this is one particular x belonging to n. Look at the product of this Cx, x belonging to n, this multiplication of this kind of these boxes. So if you have this thing, f of x is so f is a function which is a map from n to f, then one particular value you will lie in exactly one of these intervals. So we can identify the whole f with the action on the point where it is being taken. So rest all intervals would be of no use. If x is there, then it is cx. If it is y, then that is cy, exactly one value. So f can be identified with a infinite tuple, if n is infinite, or if it is with a tuple in product of cx. So f gets identified with an tuple in the space cx, product of cx, x belonging to n. It is identified with this thing. So this f was in fact an object in S star. So what do we have is that we have found out a mapping which sends a function to this space product of cx if the space is what? Real space. So a function identified with an array over here. Okay, so this is the way how S star gets embedded in this product of Cx space. So these are the product of intervals, closed intervals. Now what is this topology on this space? If we call this thing as C, what topology shall we put? So each of this is having already the topology, the subspace topology which is coming from the real line, which is here minus norm of x to norm of x, the closed interval. It's having a topology which is endowed as a subspace topology from R to multiply these things. So there are two ways. The one is the box topology and another is the product topology. So what is the product topology? In a product topology, a typical open set would be what? Product of open sets, but only finite many things will not be the whole of the set. So only finite many entries can be not whole of the space real line R. Or in this case, that is the, yeah, so in the case of this R. So the point is that each of the Cx is a closed subspace, and not only that, it's a Hausdorff subspace, it's also compact subspace in R. So so it's a compact subspace. So each of the Cx, so observe that Cx is compact in R. Cx is compact in R. The moment Cx is compact in R, So if we apply this Cx, so it's having a topology of this thing, and we put the product topology on this thing. So the space C becomes what? So we are using the Tikhonov theorem. So if we use the Tikhonov theorem, then what do we get? The product of apply Tikhonov's theorem. So what do we get? Arbitrary product of, so arbitrary product of compact spaces is compact in product topology. Arbitrary product. So arbitrary product of compact spaces is compact. So if you end out, so C is a compact space and S star is embedded, or there is an injective map in this C. So what we try to show is that S star is in fact a closed. So this kind of identification of the functions what we are having as an array what we have identified, then we show that you take a limit point in of S star, which is of S star bar, then in fact that is what in S star, that is what we will show. So if F is a complex field, then what do we have? If F is a complex field, then what we get is that the condition mod of f of x less than equal to norm of x, 1 times norm of x. So let's write that condition also. So in that case, what it would be? So if our field is a set of complex numbers, then f belonging to S star would imply that mod of f of x is less than equal to norm of x. Now this modulus is a modulus of a complex number. And hence what do we get? Once it's a modulus of a complex number, so we have to consider the disks, consider all z belonging to C such that mod of z is less than equal to norm x. So this would be our Cx in this case, and we will again consider product of Cx, where Cx is this is the closed disk centered at what point? Centered at 0. The distance of z minus 0 is what? That is the thing. So this again Cx is Cx is clearly a compact in C, subspace of C. Of C. So again arbitrary product of compact spaces is compact. So what do we get is that this is in fact a compact space. This is a compact space, and again the same kind of embedding is there. F can be identified with an array over here. So Tikhonov's theorem and so on. So let's start with the closure of S star. Okay. Now S star is embedded here. What it is clear to see is that the subspace topology, if we put on the product topology what we are putting over here as an embedding what f of x is there, so the subspace topology, it is in fact the same thing as the weak star topology on S star. So the weak star topology on S star is the subspace topology on the embedding. So both of the topologies coincide. Every open set in this as a subspace topology of this compact subspace is the same thing as the weak star topology on S star. Let's look at this fact. S star bar in weak star topology, you say, or in the as a subspace of the identification of this point of one particular f and so on, one array and so on, so subspace of C. So if G belongs to S star bar, that implies G is a limit point of S star. G is the limit point of S star. That is the case. So if G is the limit point of S star, so every neighborhood of G intersects S star. Okay. And what do we have? Since G is in S star and S star, this kind of embedding we have, so it's clear to see that mod of G of x is less than equal to norm of x, because G is an object in C and C is nothing but product. If it is real number, it is the product of those closed interval minus norm x to norm x, or the disks with the radius norm x around 0 and so on. So this shows that G is in fact what? G is in fact is having this kind of a bound. So if we show that G is linear, so that would become, so this is satisfying a definition of boundedness in a bounded linear setting. So the point is that what we need to show, so we need to show that G is in fact a linear map. Now you look at any epsilon neighborhood. So let epsilon be greater than 0. Consider so epsilon by 3, that is also greater than 0. So you consider the epsilon by 3 neighborhood of G. That intersects what? That intersects S star. So let's write that. So that means the following. So if you consider this thing, so there exists a f belonging to S star such that for all x, what would happen is that minus f of x is strictly less than x is anything in n, we can take it y also. Minus f of y would also be less than epsilon by 3, and also g of x plus y minus f of x plus y, because n is a non-linear space, x and y belonging to n would imply x plus y belongs to n. It's a non-linear, so this is also less than epsilon by 3. So what do we get? We get that g of x plus y minus f of x plus y would be what? Would be that. So norm of g of x plus y minus f of x minus f of y, because f is linear, f is in S star, this is epsilon by 3. So if you consider the following object, what is that? G of x plus y minus gx minus g of y. This, add and subtract the terms fx, fy, fx plus y. So f plus fx minus fx plus fy minus fy plus f of x plus y minus of f of x plus y. So this would be, and using all of this thing, strictly less than this term, this term, this term. So that would be less than strictly epsilon by 3 plus epsilon by 3 plus epsilon by 3. So this is equal to what? Epsilon. And since epsilon is arbitrary, what do we get? Is that g of x plus y becomes g of x plus g of y. So which shows one half property of the linearity. So if alpha is any scalar, then it can be similarly shown that it is what? It is in fact that g of alpha x is also alpha times g of x. So what would happen is that you can suitably scale alpha, every neighborhood of g intersects S star because g is the limit point. So this shows that g is linear and it is also continuous. Okay. So what we have is that the another proposition which says that if n is a non-linear space and S star is the compact Hausdorff space. So this is an established fact that what we have shown, it's a compact Hausdorff space in the weak star topology, the closed unit sphere. Then, so what do we have? We have another identification in n star star. So x is going to capital F subscript x. So capital F subscript x on f is fx for each f in S star. In fact, it is in for n star also. So this, if you restrict it to S star, so what we see is that not only that is an isometric isomorphism. So let's write that. So a compact Hausdorff space CS star. This proposition also proves the following fact is that n, this is the space, this is the compact Hausdorff space CS star. Okay, so if n is a Banach space, then we have the mapping as isometric isomorphism of n onto a closed linear subspace of CS star. So this is all maps from, so the identification is clear. So C of S star is the continuous maps from S star to S star. So what we want to prove is the open mapping theorem. Which states that if you have two Banach spaces and a map between them, you have these two things, and you have a T as a map from B to B dash. If T is linear as well as a continuous, then also further is that T is onto map. Okay. So let's write that T linear, T continuous, T onto. Then this says that T is an open map. That is, it takes open sets to open sets. The point is that inverse image, so if you look at T, inverse image of open set is always open because T is given to be what? Continuous. What does this say? If you have an onto linear continuous map or onto linear map continuous also, then the image of an open set is also open set. So if you have T which is 1 1 onto linear continuous between two Banach spaces, then by this proposition it would also be an open map. And if it is an open map, So if you look at the inverse map, because it is in 1 1 on 2, so inverse function from, so B to B dash. So if T is a map from B to B dash onto 1 1, linear, continuous, okay. So T inverse would exist, which would be mapped from B dash to B, which will also be 1 1 on 2, okay, linear also. Then what do we have is that T inverse is also continuous. Is also continuous. In fact, it's a homeomorphism. Okay. So if T of x plus y, we know that is Tx plus Ty. So if U is let's clearly see that it's T inverse is a linear map. So T inverse of U plus V would be what? If it is some value, maybe say R, then U plus V is a T of R, and it's a 1 1 on 2, so R is unique. So U plus V is T of R, but U, because it is an onto map, U itself is something which is what maybe say T inverse of W plus T inverse of H, it would be T of R. So T inverse of this thing, T inverse of this thing, R is nothing but T inverse. So T of R is U plus V. So U is nothing but U plus V. So T of R is U plus V, T inverse W, T inverse of H. And then if you apply T inverse of this thing, R is nothing but T inverse of U plus V. So applying taking T inverse, so what do we get is that T inverse of this object over here, that would be U plus V, and U itself is T inverse of W and T inverse of H. So this open mapping theorem helps for 1 1 on 2 map, which are linear and continuous, to make linear, and the inverse is also becoming continuous. So it is in fact becoming a homeomorphism. So an onto map between two Banach spaces, which is linear and continuous, is in fact an open map. It maps an open map to an open map. Sorry, open sets to an open set. Inverse image of an open set is always an open, because given it is continuous, the topological definition of continuity. So before that, prove in part. So first lemma, which is required to prove this thing. So let T be a map from B to B dash. B and B dash are Banach spaces. T is given to be linear. T is also given to be continuous. Then the claim is that the image of an open ball centered at 0 with a radius R contains 0 of B dash as an interior point. This is important. So what we are saying is that suppose SR is a ball centered at 0 with radius R, R is strictly greater than 0. You look at this SR and look at TSR. Then 0 is in fact what? An interior point of TSR. It's inside, not only it's there, it's not lying on the boundary or outside, it is in fact an interior point. So let's try to show this thing. proof of the following fact. So SR is the collection of all those x belonging to B such that norm of x is strictly less than R. Okay. SR dash, first of all, SR is a subset of B. Okay. Another notation, SR dash, collection of all U belonging to the right hand side, which is B dash, is that norm of U is strictly less than R. Where R is a real number or strictly greater than 0. So we have these things. SR dash, so it's a ball centered at 0 with positive radius in B, ball centered at 0 with positive radius in B dash. So what do we have? SR dash. So we are looking at TSR. So the claim is that R is any real number, then TSR, what we want to show, is an interior point. Is an interior. Rather, 0 is an interior, has point origin. Another one. The origin. Okay. So because the map is on to what we have the following, is that observe that B dash can be written as union of TSN, n going from 1 to infinity. So TS1 would be what? As a set, TS1 is T of x such that x belongs to B and norm of x strictly less than 1. This is TS1. So what would be TS2? TS2 would be nothing but collection of all those Tx such that x is in B and norm of x is strictly less than B. What would be TS3? TS3 would be collection of T of x. All x belong to B such that norm of x is strictly less than 3. So the point is that every point, since the map is onto, so T is given to be an onto map. So every object has a pre-image. So if the object has a pre-image, then T of x would be what? So T is a map from B to B dash, and it is given to be an onto map. So if you take any U belonging to B dash, then what do we have? We have that there exists a, rather say y belonging to B such that T of y is equal to U. Now since the object, so TS1 and so on, so every object would be what is clearly from this fact it is that the union is clearly easy to see, that why it is TS1 union TS2 union TS3, every point has a pre-image. So if you take the S1, S2, S3 and so on, the union of these SIs is in fact B. So if you look at TS1, TS2, TS3 and so on, that would make it what? So every object is there. So in B, if you take any x, maybe say any x belonging to B, so norm of x is a fixed real number, maybe say whatever. If it is equal to T, then it is strictly less than, it's clearly easy to see that x belongs to S T plus 1. It is strictly less than what? T plus 1. So because of this fact, and every object would have a pre-image, so it would be some number, any that number is there. So if T belonging to what? Natural number. If T is a real number, what we can do is that we can look at the integral part. So any the integer, positive integer closest to T. If it is not a natural number, if T is in R, what we can do is that we can look at the integer part of T. Plus 1 in this case. Okay. And you can easily, so from here it's an easily to see fact that what it is, that B dash is what? Union of T Sn n going from 1 to infinity. So images, if you take and take the union of Tsn, so Ts1, Ts2, Ts3 and so on, it forms an image. Now B dash is given to be what? Given to be a Banach space. So B dash is given to be a Banach space. It's what kind of, so it's every Cauchy sequence converges. So it's a category 2 space. So we'll apply here the Bere category theorem. Category theorem. What does it give? The Bere category theorem gives that if you have a complete metric space and you write it as a countable union of sets, then at least one of the set must not be nowhere dense set. In other words, a category 2 space cannot be written as a countable union of nowhere dense set. So if a complete metric space is a union of some sets, at least one of the sets which is occurring in the union must not be nowhere dense set, and hence what happens is that because it has a non-empty interior, we can claim that there exists a n naught belonging to set of natural numbers such that what happens? The closure of T Sn naught is, if you look at this set, it's interior. This is not empty. The closure of Tsn, the interior of Tsn naught bar. This is in fact a non. The interior of this set is non-empty. Right. The moment you have this thing, so it has an interior point. So T Sn naught bar has an interior point. In other words, you can find so Y naught is an interior point of Tsn naught bar. So let's call by the name Y naught. Since it's a closure of a set, we can assume that Y naught is in fact an interior point of Tsn naught. If you consider the mapping, we have B dash to B dash sending object Y to Y minus Y naught. So you are just subtracting y0 from every element here. So this map, if you can see, is clearly a 1-1 map onto map, continuous map, as yn, suppose yn is a sequence which converges to w, then yn minus y0 converges to w minus y0, and the inverse is also continuous. The inverse mapping is the reverse mapping, which is sending maybe say h to h plus y0. This is the inverse mapping. So it's in fact a homomorphism. So we are assuming now, without loss of generality, as we have shown there, Tsn naught. In fact, it's an interior point of Tsn naught. So if we consider the following object, Tsn naught bar minus y0 as a set, this object is contained in Tsn naught minus y0, the closure of this thing. This is the closure of this set minus the point. So you are taking a point here and subtracting y0. These all objects are in B dash, and so on. So what do we get is that from here, since y0 is in Tsn naught, so as a set, so if you look at Tsn naught and Tsn naught, so you subtract these two things. So what happens is that the diameter of this set would be what? You did this difference of a point whose, so if any object is there in Tsn naught, maybe say y, then it is some t of x, and norm of x is less than, strictly less than n naught. So this and this is clearly contained in Ts2n naught. So the diameter of this set Tsn naught, so one can see. So the point is that Tsn naught minus y0, this closure is contained in Ts2n naught, its closure. The scaling, so Ts2n naught, so if you scale any vector, so if you take any non-zero vector over here, we can have what? We can scale the vector to be one unit vector by dividing its norm. So it's Ts2n naught is nothing but 2n naught times Ts1. So the closure of Ts2n naught is nothing but 2n naught Ts1, its closure. Okay. Now since y0 is an interior point of Tsn naught and so on, so y0 is also an interior point of this set, so of this one. So y0, as y0 is in Tsn naught, so y0 minus y0 is in Tsn naught. So what do we get is that the 0 is the interior point of what? Of this set here. What do we get is that 0 is an interior point of Ts1 bar. Zero is an interior point of TS1 bar. So there exists a epsilon greater than 0 such that S epsilon dash, which is a ball centered at 0 with radius epsilon, is contained in what? TS1 bar. This is. Now the point here is that this is a closure of the set. So what do we get is that S epsilon dash is contained in this set, but in fact we want to show that 0 is an interior point of the image of some ball. So we'll show that TS3 will in fact show that S epsilon dash is contained in TS3. Okay. So take a point. So what do we have? TS1 bar. Let y1, or rather y, belonging to S epsilon dash. This implies that y belongs to TS1 bar. If y belongs to TS1 bar, that means that y is an limit point, of the set TS1. So there exists there is any neighborhood of y, or any open set of y intersects TS1. So you take the epsilon neighborhood of, and since y belongs to S epsilon dash, this implies that norm of y is strictly less than epsilon. And y is also in what? TS1 bar. There exists a x1 belonging to B such that norm of x1 strictly less than 1 and T of x1 is equal to y1 norm of y minus y1 strictly less than epsilon by 2. So this is the epsilon by 2 neighborhood by 2 radius ball, open ball centered at y. So it intersects TS1 y1 in a point other than y. So such a point we are calling it as y1, and y1 would be tx1, which is above. So epsilon by 2 neighborhood. So since the norm of y minus y1 is an epsilon by 2, and the distance of, if you look at this object from 0, the norm of y minus y1 minus 0, that is epsilon by 2. So the point is that this point, and epsilon by 2 is strictly less than epsilon, so this point y minus y1 is also in epsilon dash. Okay, so y minus y1 is in fact in what ball? If we had that epsilon there, so S epsilon by 2 dash. And again by scaling, what we have, that S epsilon dash is contained in what? Is contained in TS1 bar. So S epsilon by 2 would be contained in T, just by scaling TS1 2 bar. Okay. So the same argument here. Now if we apply, what do we get is that in spite of y, this is replaced with y minus y1. Epsilon is replaced with epsilon by 2. Norm of y will be replaced by norm of y minus y1, that is epsilon by 2. So the whole argument here would be just replacing this thing. So this is y minus y1 y minus y1 epsilon by 2. Here it would be 2 and here would be y minus y1. There exists a x2 such that norm of this is strictly less than this half is there, so this is half over here. And now tx2 will be y2, and this object would become norm of y minus y1 minus y2. This would be epsilon by 4. So if you take epsilon by 4 neighborhood of the point y minus y1 that intersects, so that intersects non-trivially, so what do we get is y minus y1 minus y2 is strictly less than epsilon by 4. So this is epsilon by 4, radius open bond centered at y minus y1. It intersects ts half in a point other than y minus y1, that is the point y2 is t of x2. So we get this thing, and the distance, again the distance between them, so this is contained, so epsilon by 4 is contained in epsilon by 2 is contained in epsilon, so this point is also in s epsilon dash. So here we will have y minus y1 minus y2 minus 0, that is strictly less than what? Epsilon by 4. So s because this argument was for half also, so what do we get here is that s epsilon by dash 4 is contained in what? S1 by 4. So we have as a point y is contained in ts1 bar, y minus y1 is contained in ts half bar, y minus y1 minus y2 is contained in t, that would be contained in now what? ts1 by 4. And so on. So let's write that with the scalings and so on. Y is contained in ts1 bar, y minus y1 is contained in ts half whole bar, where norm of x1 is strictly less than 1 and t of x1 is equal to y1, and norm of y1 norm of rather this y minus y1 is strictly less than epsilon by 2. Here norm of y strictly less than epsilon. Then again with epsilon, so this is looking at here, then epsilon by 2 ball, epsilon by 4 ball, so y minus y1 minus y2. So this object belongs to ts1 by 4 bar. There exists a x2 such that norm of x2 is strictly less than half, and norm of y minus y1 minus y2 is strictly less than epsilon by 4, and t of x2 is equal to y2. Okay. So what do we get? Is that this sequence, we have this thing, so norm of x1 strictly less than 1, norm of x2 strictly less than half, norm of x3 strictly less than 1 by 4, and continuing. So norm of xn is strictly less than 1 upon 2 raised to n minus 1, and while norm of y is what? Strictly less than epsilon, norm of y1 strictly less than epsilon by 2, and norm of y minus y1 rather, y minus y1 is strictly less than epsilon by 2. The third term would be norm of y minus y1 minus y2, that would be strictly less than epsilon by 4. So in general, if you have the nth term y minus y1 up till maybe say yn, that would be strictly less than epsilon by 2 raised to n, because there are n plus 1 terms and so on. So norm of xn is strictly less than 1 upon 2 raised to n minus 1 from y, these n terms and y, this subtraction is epsilon by 2 raised to n. And t of x1 is y1, t of x2 is y2, and so on, so on, so on. So what do we get? We get that let x is equal to x1 xn. So t of x tx1 txn, which is nothing but y1 plus yn. So y minus t of x, if you look at the norm of this thing, this is strictly less than epsilon upon 2 raised to n. Okay. And y1 is t of x1 and so on. Okay. So if we call this as x, rather we'll just change the term as the sum of the n terms. So let's call this thing as Sn, the partial term of the series Sn. So Tsn. So in other words, as n tends to infinity, we can clearly see that each of this Tsn, because it's this sequence Tsn is converging to y. Okay. And so the sequence Tsn converges to y. As n tends to infinity, this tends to 0. So if you consider the norm of Sn, norm of Sn is nothing but norm of x1 xn, its norm, that is strictly less than equal to triangle inequality, norm x1 plus norm xn. Okay. So this is what norm of xn is, strictly less than 1 plus half 1 upon 2 raised to n minus 1. This is a geometrical sum starting with 1. So this is what strictly the sum of this series is what 1 minus 1 by 2 raised to n and so on. So adding some terms. So this will be strictly less than 1 upon 1 by 2. So this is strictly less than